Good evening, YouTubers. Today we're going to be discussing what is called a fed batch reactor, and basically it's an adiabatic reactor. So let's say that it has a protected cover that will not allow heat to be exchanged with the environment. So that's what we call it's going to be an adiabatic tank. Basically that's what we're gonna have, an adiabatic tank. But this is a fed batch reactor, so there's gonna be some input into it. Something's gonna be added, and we have something here, sort of like let's say water. We have water here at a given temperature. We're gonna do a kind of a quick simulation here. Let me erase this. So let's say that we have a mass, actually must be better, an a mass, an initial mass, and also we have an initial temperature inside this tank, and we're going to be adding in a controlled fashion some cooling media inside. So the mass will change, and so the temperature, there we go. So let's say this is gonna be at a temperature T1, and inside is a different temperature. So we're gonna control the addition of that. So we're gonna measure, we're gonna have a TI, a controller, and from here we're gonna go to the valve to control the flow. So, and we're gonna have here a set point. So that's what we want to do. We're gonna be adding a liquid to cool this reaction to a given set point, and the flow will be controlled by this controller. So the first thing that we're going to try to understand is the model, the system model. Let's call, what is the system model or the math model that will describe this batch reactor? Basically, we're going to start by saying, hey, the energy that is getting into this reactor somehow is going to be the mass flow that this valve allows. So let's call that m dot. So we're going to have m dot times Cp times the temperature of that addition. Now remember, this is an energy term that needs to be with a reference, to a given reference. So it actually is like T1 minus a T reference. We're going to talk about the reference at a later time, but for now let's say that this is the energy getting into or the flow of energy. So we will multiply that by delta T, a small amount of time. Then we go the energy that got in, that impact whatever we have here. Since it's adiabatic, I don't have to worry about anything else except that this has to be equal to the change of energy inside here. So that means that we're going to have an mCp. The inside temperature happen to be also against some reference. We need to do some reference here, T minus T reference, and all this term is measured at T plus delta T minus mCp T minus T reference, but then all this term has to be measured at time T. So what's going to happen is, if you divide by delta T both sides, then you end up by having mCp T1 minus T reference equal, and here we go, the limit of delta T approach 0. This is called this is the definition of first derivative. So that means that we end up with actually let's write it this way, the differential with respect to time of all this term, mCp T minus T reference, close and close. So the only thing that we need to do is to take this differential, and to do that, remember that, just write it here, that m is a function of time as well. Actually, let me write it this way, m is a function of time, and t is also, let's call this f1 and f2, is a function of time as well. Both change, so we end up having here is sort of like a chain rule. And to do that, then we end up with m dot cp t1 minus t reference equal, now cp is a constant, so we can take the cp out, and we end up with the derivative of the term m times, let's write it like this, t minus t reference, and close this out. So let me work only on this part here. So we end up having cp the calorific constant, then let's take the first derivative times this as a constant, so that would be t minus t reference find the derivative of m with respect to time, plus, again, let's open here so that the cp stay out, then plus the derivative of this part here times m, so it's going to be m times the derivative with respect to time of t minus t reference. Close here. Now what we're going to have now is cp times t minus t reference dm dt plus the derivative of this part here, so that will be m, that would be m, let's say that t reference is a number, and we end up by having something like this, m dt dt. If this is a constant, the derivative will be 0, and we end up with this equation. Close the parentheses, and we bring the other stuff back, m cp t1 minus t reference, and here we go. One thing that we could do is t minus t reference. What's going to be a good reference temperature? Actually, these are some of those cases that it makes sense to leave t reference, now that we clear the whole thing, equal to t. If we do that, then we end up having mcp t1 minus t equal cp. Now t equal t reference, and this t is equal to that as well. This is gone, and we're gonna end up with cp m change temperature with respect to time. So the differential equation end up like this, m dot cp t1 minus t over, let's take this mcp, and finally the cp cancel out, and we end up that this is the differential equation that describe how the temperature will change in that vessel. For a I mean, there's no reaction in this vessel. I'm only adding a fluid, in this case, like for example water, to cool this content, which is also, they have both the same cp value. All right, so with that clear, then we end up with this equation. Now, since you are adding material into this vessel, what's going to happen is the mass will change as well, but that's easy, because the chain of mass in this vessel is going to be equal to m dot. That's basically it. The mass getting into the tank. So we end up with our second equation. So now we have these two equations, these two differential equations. Now these two differential equations can be used for two things. One of them is called dynamics. Dynamics, we're gonna have t M, and temperature. At time equals 0, the mass is the initial mass within the vessel. Let's say that we are working with a very small tanks or reactor, something like a lab experiment, and let's say that the mass is about 800 grams, and that the temperature is kind of hot water, about 80 degrees C. And those are the initial conditions. If I keep working on these, like 0, 10, let's say that the delta T for my Euler method will be about 10 seconds, then we can integrate both of these equations using the Euler method. That would be straightforward, because basically for if I can do it here, the integrated version of this would be like T plus delta T equal T at a given time plus delta T times m dot over m T1 minus T, and this version here will be m T plus delta T equal mt plus delta T times m dot. So we can use both definitions of Euler method and get this going. Like, I can do it here. Actually, I'm gonna do it here for one calculation, but then we move to Excel, because that would be the way to do this. So, like for example, let's say that I'm interested in the mass at 800 the mass at 10 seconds. What's going to be the new mass here, and what's going to be the new temperature here? Then you use this the Euler part. Like for example, what's going to be the mass? That's straightforward. The new mass is going to be the old mass, which is 800, plus whatever flow rate I established here, and that has to be coming from that value of m1. What will be m1? Let's say that m1 is a small number. Let's say that it's about 2.5 grams per second. So we end up having 2.5 grams per second. Let's put the unit here and multiply by 10 seconds. So second cancel out, and we end up that the mass is about 800 plus 25, or 825 grams. So that's what we end up here, having 825 grams, because I adjusted the flow into the vessel to about 2.5 grams per second. Now, how about the temperature? Then we use this one here. The new temperature is going to be the old temperature plus 10 times m dot, which is 2.5, divided by the old mass, which is 800, and that multiplied by T1. Well, what is T1? T1 is the input temperature, the temperature of the cold water getting into the vessel. Let's say that T1 for this experiment is going to be set at 20 degrees C. That means that I have here 20 minus the initial temperature, since we established that to be at 80, so that's going to be this here. So the new temperature will be, let's get a calculator here somewhere, 10 times 2.5 divided by 100, multiply by the difference of 20 minus 80, that's going to be minus 60. Let's say 60 times 60, that's 1.85. That's 1.875. So this means 80 minus 1.875, and the difference is 78. So that's the new temperature. And so we delete this, and that's what you have. Now the idea is to carry this on until we get the curve, the full curve for this, particularly temperature versus time. So that will provide us, again, this, remember, this is dynamics. I'm not talking about control, I'm talking about dynamics at this point. That will give us a curve that might look like this. Like for example, starting at 80 degrees, and you are cooling this off or you have a curve like this, which eventually will tailor down asymptotic to about the temperature that is getting into the vessel. That's about 20 degrees C. So you got 80 to 20. So what's the story about having this curve? Well, this curve is important for the calculation of what we call Kc, which is the proportional constant. The proportional constant for, obviously, for the proportional controller. That's going to be written like this, right? You remember, CO equals CO bias plus, I'm going to put plus, but remember that Kc has a sign, very important. Here is set point minus the process variable. So on this equation, we definitely need to know what is the value of Kc. So by doing this, what we call dynamics. In dynamics, it's a manual run. Basically, in this manual run, you set a value of the material getting into the reactor. We set it to 2.5 and we produce this curve. Obviously, if this number is higher, it will produce a faster cooling. If it's lower, it's going to produce a slower than rate of descent. So the question is, how can we calculate Kc only with running this curve at what it looks like at 50% of the maximum flow rate? Let's understand what I'm saying here. Like how I put this value on 2.5. Let's talk about 1 second on that value. Basically, what I was saying is that the maximum flow, actually, let's write it this way. Let's call that maximum flow. I set that value, let's say, to 5 grams per second. Now, I'm gonna set the bias, so I'm gonna establish a value for this manual run at 50%. Means that the actual M flow, or M dot, which is mass flow, the actual flow will be about 5 grams maximum times 50% divided by 100, and that will give us 2.5 grams per second. So in other words, we are changing from 0 to 50% to do this run, because basically at 80 degrees there's no flow into the vessel. But as soon as I change to 50%, which is 2.5 grams per second, then the temperature will start to drop until eventually it hit the 20 degrees, which is the input temperature. Now, from this type of curve, in order to calculate Kc, I need 2 important parameters. Let's talk about them. For example, Kc is basically 1 over a value that is known as Kp times the temperature, time 1 over Kp times the time of 63% change in the curve divided by the time of 28% change in the curve, and all that elevated to 1.22. So that's the equation that I'm going to be using for my calculation of Kc. So the question is, what is Kp? Well, Kp is the process gain, how sensitive this process is. Like, it's calculated like this: delta PV, the change in the process variable from one value to another, divided by the change of CO. What that really means is the PV final on this study minus PV initial divided by CO final minus CO initial. As you can see, basically I'm going from 80 to about 20 by adding cold water. That will take a while, right? So and here in this axle I have time. So I have an idea what that Kp will be. It's simple as doing this. Like, what is the PV final? Is actually 20. What is the initial? 80, and all that. What is the final? 50. What is the initial? Starts 0. So we end up that Kp for this particular run is going to be minus 60 divided by 50, or negative 1.2. Now kp has units. The unit of kp obviously is degrees C divided by percentage. Now I have kp. How can I get T63% of change and T of 28, which are time? These are time. Now without going deep into the whole story, let me show the mechanics of how you get that. In order to get the T of 63% in this curve, this is the curve, this is a manual curve, and I'm basically kind of using what is called Cohen-Kuhn method. It's an open loop, basically what I'm using, a steady state, analyzing this, kind of going into from one point to another to a steady state. That's basically what I'm doing, and for this case, for this particular case. So with that said, T of 63, what I'm trying to get is, this is based on PV of 63% change, and that would be PV initial plus delta PV times 0.63, and that will hit a number. How about T of 28%? You do the same. PV of 28% is going to be PV initial plus delta PV times 0.28. Sorry for it. That will give you a number. So these are the two equations that I need to calculate both of this time. How much time it takes the system to get about 63% of the total change versus how much it takes to get to the 28%. And this here is more related to something that is called later dead time or lag time. All right, and so what we're going to do now is we're going to develop this. We're going to go to Excel and calculate this dynamic, and when we calculate the dynamic, then we're going to go and take a look to this equation, and finally use those equations to calculate Kc. So that's what we're going to do. Trying to run this manually is it's not fun. So we're gonna do this on Excel. It's very straightforward, and do the calculation basically for how to get the T63 and the T28, and also from Excel, and finally get the Kc value. So let's move now to Excel to get this second part, which is how we calculate Kc value now that we have a model, basically a model which are based on, this move is based on these two equations. Our model is based on this. One differential equation for the temperature inside the tank. There's no reaction, so there's no heat of reaction here included, as you don't need it, but there's addition of material, so the mass inside the vessel is changing. So now, second part, we move to Excel to get the dynamic, and then there's going to be a third part that based on that Kc value calculated on the dynamic, then we do some theoretical control, and let's see how that will produce some good results. See you now in the second part. So here we are for the second part. As always, try to get all your numbers in a decent way. Like for example, parameters, we have the initial mass. It's a small reactor, as I said, small lab experiment with 800 grams. Initial temperature about 80. T1 is the temperature that is coming from the cold water. It's about 20 degrees. The CO bias for this dynamic will be set to 50. Before T equals 0 is 0. There's no CO bias. You impose this, and that will regulate this maximum mass flow, which was set at 5 grams per second. So you end up with an actual mass m dot 2.5 grams per second. We're going to use a delta T of 10 seconds. So basically that will generate this equation here. At time 0 we have 800. You come from that before is right here. And how about the T? The T is come from here as well, B5. Now this one here, careful here, let me see if I can increase this a little bit so you know what is inside. Alright, so like for example here is A13, which is the one above, plus 10. So if you drag this, you will see 10, 10, 20, 30, 40. You see, but it's $10. $10 is the delta T. So that's perfect. Enter. How about what I have here? Then here I have the, that's coming from the Euler method. For the mass is the original mass 800 here plus this $10 is that delta T times $9. That's the flow, m dot. So that provide that number there, 825. How about this temperature here? That's the full equation. I show you about temperature. It's the initial temperature, this one here, time $9, that's a fixed value of 2.5, divided by the mass, which is changing, that's coming from here, multiplied by the difference in temperature, T1, $6 minus C13, this temperature here, right, which is the same as this one, C13, time delta T, $10. That's perfect. Input. Now we drag those values down, and when you do that, you can drag them, and you see the temperature coming down, 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 until finally you get to a value of, you can keep doing this. I mean, it will keep dropping. I mean, but they will not change much the final result, and you will see why in a second. Let's get this going. Let's see if I can get this. Yeah, let it go. See, almost about 3 hours later, and still 21.88. So it's not moving that quick, but it will eventually hit that. So, but in the meantime, the only thing that is important is taking a look to this graph the way it is right now. There we go. I'm not adding more point into it, but I'm just saying that I know that eventually when I calculate this delta PV, it's going to be minus 60, because basically it's the difference of temperature of whatever cold water I'm using, that's B6, minus the initial temperature that is called B5, and that gives you the minus 60. So delta PV for this equation here, both of them will be using the minus 60. The question is, what is PV of 63%? Then you have to use this one here, which is the initial PV, that's B5, 80, plus F3 is this minus 60, multiplied by 0.63, so that dropped the temperature from from 80, it dropped it to 63.2, or in this case 42.2. This is the one that we were talking about, 42.2. That means that the only thing that you need to look is for that particular temperature of 42.2, and you look for the time where that happened, 42.2. Between these two guys, 42.2, basically you can more or less say that this is the value somewhere there, and that will give you 530. So that's the time of what we call T63 is 530 right here. Now the other time that I need is the one that happened at 63.2 on the PV. So we look again for the column of 63.2. Let me reduce this so that I can see more. $63.2. We're looking for 63.2. 63.2. This will be 63.3, 63.2. That's the closest value. Somehow you can, you can start to look for interpolation, but at this point it's not worth it. It is a value that eventually you will know why it's not worth it, but it's not required to be that accurate. Imagine you are looking for those numbers here in the graph, so that would be harder, but that's what I'm using the table. So basically trying to hit that 63.2 coming down here. The most close to it is I would say 120, which is what I have there. Now for the calculation of KP, it's basically, let's see if I got it here, it's gonna be that delta PV, that's minus 60 divided by B7, that's the CO bias, and that give you negative 1.2, and eventually you get the calculation of KC. Let's drop here inside, so it's 1 over F6, which is this value here, 1 of negative 1.2, and that's going to be E4 over E5. E4 is this guy here over E5 is this guy here, and that ratio is elevated to 1.22, and bingo, you have the value of KC for this run. You can, again, maybe you can have the different flow rate here and see how much this value can be adjusted depending on what flow rate you expect to have. I'm right in the middle with the 50%, and so you end up about negative 0.5.1. This negative is very important. It's telling me that this is a direct process, and if I go back to let's see where I'm here. If I go back here, basically, if the temperature, for example, if the temperature for any reason here start to increase, we call that PV. What you have to do with this valve, the output from the controller gotta increase that valve to control this issue, so you end up having both in the same direction. That means it's direct acting. You have a direct acting, meaning that the KC has to be negative, which is basically what you see in the Excel calculation. So we end up with a negative value of 5.1, for testing. So sometimes I use like a factor of 2 above and 2 below, and see how well the model behave. Remember, these are ideas before you going into the actual experiment, so you have a very good idea of where the numbers are to try to do the experiment as close as possible and be aligned with the theory. Well, folks, this ends the second part, so now we are ready for the third and last part, which have to do with control. This was dynamic, and the only thing about dynamic was how to get those particular time of PV of 63, of T of 63% and changes of 28% of this whole curve, and with that we calculate the KC value. Now with that done, we are ready now to do control, which is the third part of this video. See you in a moment. Alright, so this is the third part of this video, and this is the process control, and let me get this right here. So we identify this, so we are here in process control, in where basically we want a particular set point of 40 degrees. We start with water in the reactor at 80. We're gonna cool that with 20 as a fed batch reactor, and as you can see, the CO bias is 0 for this run, and the mass flow is 5 grams per second as before, and that is going to be 0 to start with, but it's going to be adjusted in the run. Delta T is going to be 10, the set point is going to be 40, and the KC value is minus 5 as calculated last time, and you end up with this table in where you have time, the error, the value that you calculate, and that value needs to be corrected. If it's above 100, you set to 100. If it's below 0, you set to 0 as shown here, and the mass flow and the total mass in the reactor according to the flow that you're using and need to be adjusted, and eventually the temperature within the reactor. Now let's see, here we are, we start at 0, and basically these two values come from the above, from this table above, like the 880, but then you use Euler and to calculate everything else. But before doing that, let's finish the first line. So this line is 0. Now when you have this value of 80, the correction that you need to do is what is the set point? Is 40. Set point PV, the set point, that's 40 minus 80, that's gonna give you a negative number of minus 40. Now this is gonna be the bias $6, but that's 0 at this point, plus $11, that's the Kc value times the error, that gives you 200. That's obviously not possible, so you recalculate that to 100 using this formula here. Let me punch this. This is a Spanish version of Excel. I don't know where I get this from, but as you can see, it's SI meaning C, or if. That's a if this is the formula that looks like to get this into corrected automatically, you know, so that the numbers stay with 0 as a minimum, 100 to a maximum. And this is the mass flow, which is going to be adjusted by this value. So if this is 100%, it means that I want full, you know, the full mass flow of 5 grams per second on this small tiny reactor. And these are the initial values. So the next thing that we need to do is, like, we go for the second line. Obviously, as you can see, this line has the automatic addition of the delta T, which is about 10, $9. Now we calculate these two guys. These two need to be calculated by Euler method, and it's pretty much identical to what we did on dynamic, except that the value here are coming from actually from the table, including both, like the mass flow and the mass within inside the vessel, which are these two values here. Now the temperature come from here, and this is delta T, and there's nothing else here to talk about because it's pretty much the same. Now the mass here again is come from this table, not from above, because it's going to change as you get closer to the set point. It's going to get smaller and smaller until it just reduces it to 0, fully automated. There we go. So we got that, and as you can see, for the next line, the error dropped to 36. Now if I keep, you know, dragging this, eventually you see that the error here on this column gets smaller and smaller, and the flow after 70 seconds start to get smaller. Instead of the pi, start to 4.78, 439, 4377, gets smaller and smaller. Remember, the set point is 40. We're looking for the 40, and within the several minutes, pretty much there, and the error getting smaller and smaller as we go, until eventually the amount of material that's being added is very small, as you can see here, very tiny, and eventually got about 2 liters or so of water. I start with 800 grams, so I end up about 2,000 grams here. Pretty much the temperature is very close to the 40 now, 41, and the error is about 1 degree from what I want, where I am right now. Keep dropping this, and eventually to about 2 liters or a little bit more than 2 liters, you end up about 1,000 minute or so. You are pretty much at the 40 degrees, depending on the error and the precision of your instrument, the temperature. So going back to the curve, you can see here that about 1,000 you are hitting the 40. Now one thing that you could do is I put here a -5. What will happen if I put a -10, like twice that value, -10, and check that out? It just got quickly to the value of the set point. I would say here with 500 or so. So it seems to me that -10 might be better. It get the job done faster. How about -20? Maybe. minus 20 seems still okay. And let's see, let's take a look here to the table itself. And it dropped to about 45 degrees at a very fast pace, and eventually it take very slowly after that. And let's see, yeah, you get to within 500, I would say 500 second. Yeah, pretty much within the error of the instrument, plus minus 0.2 degrees or so, depending on what we're going to be using a thermistor, so precision would be within that range. So definitely within 600 second, this is done. 10 minutes, we are done here. 10 minutes. If I use a very high value of minus 20, actually the actual value was minus 5 calculated at a 50%. I would say minus 10 might be a kind of another value to check. Maybe a third one would be at minus 20. So those are the three values that you might check: minus 5, minus 10, and maybe minus 20. Three values of KC to check. You know, just to see how well you control this. The important thing is that the temperature cannot go below. If it, if the temperature go below here, is you don't have any means to, like, going back to the piano. There's no mean, you are not hitting the reactor back. So whatever you are doing, like for example, if the temperature here drop below the set point that you want, this type of setup will not allow heating back. So that's why you have to be very careful, and that's why we are also using a proportional controller, not a proportional integral controller, a PI, not a PI controller, but only a P controller. A PI will drop below, and that's the end of it. It would not work. A PI controller is not good for this type of a scenario. It's going to be a proportional, and that's what we are using, a proportional controller to get this job done. Going back to Excel table, that basically finished this conversation. So you have everything here. This is the whole theory, the three parts of this project, which we started again. Going back to my note here, we started with the model. This is the system, the PNID of the system. We are controlling the inflow of material, the mass flow here to the vessel, and we developed the model. And the model, we have two differential equations as shown here. Those two differential equations, if you work with them and integrate them, then you can get the dynamic as shown here just by fixing the mass flow. In particular, we fix it to about 2.5 grams per second on this small reactor, and from this curve we obtain then using this equation here, like for example the KC value that we need to have on my proportional controller is based on 1 over KP, the time that it takes for the system to get to 63% change versus the T over 28% change, and that elevated to 1.22. That give you a KC. Now the KP is the gain of the process gain. It's called process gain, and with that process gain end up being about negative 1.2. This KP will follow the sign of KC. We know that KC for this system must be negative, so that's why KP end up being negative as well. So, and finally, we need also this calculation. To calculate T of 63% or T of 28%, we have to do this. Find out where the PV of 63% is located versus the PV of 28% is located. When you get that, it's easy to get those times. And if I go back to this first sheet, you can see here how we did that. So this is the dynamic, pure dynamic, and with that we calculate this KC value of around minus 5.1. I use 5, it's not a big deal, it's very close to it. So here is the three value that I propose to be tested as you run this experiment, and find out how quickly you can get to the temperature that you want. as per your set point. Well, that's more than enough, folks, and see you next time.